Okay, so this video is about hypothesis testing for a single population. We have not done hypothesis testing for two populations, so the word single might not feel meaningful yet, but that's what we're doing here. And this video is only going to use the critical value method, not the p-value method, which we will learn about later as well. So basically the idea of hypothesis testing is that you have a null hypothesis and then an alternative hypothesis. And based on the data that you collected, the data has what's called a sample statistic, which is either a mean or a population proportion. There could be other ones, but those are the ones we're learning about. And so you basically use that data, either that sample mean or that sample proportion, to conduct the test. And so over here you can see we have a couple examples. So just starting here at the bottom with a two-tailed test. A two-tailed test is when see how I'm of the school of thought that we always do that the null hypothesis is that the mean, or it could be the proportion. This diagram is using the mean as an example, but that the mean is equal to some value, and the alternative hypothesis can either be that the mean is actually not either to that value, or that the mean is greater than that value, or that the mean is less than that value. And so if we're saying that the mean is not equal to that value, we're like, well, I guess the mean could be lower or could be higher. And so what this yellow area is the rejection area, meaning if our mean is really far away from our null hypothesis mean, we're going to reject it. If the sample mean is far away, is extremely different than the null hypothesis mean, we're going to reject it. And so these alpha levels, so here we have alpha is 0.10, alpha is 0.05, or alpha is 0.01 for 1%. That's basically telling us how big our rejection region is. So for alpha of 0.01 or 1%, that means I'm going to have this is going to be, actually let me do it for the other one over here. For alpha of 0.1%, that means that our rejection region is 1% of the null distribution. So there's only if we assume the null height distribution is true, where the mean equals to that specific value, the mean is in the center. And if we get our sample mean somewhere all the way out here, under the assumption of the null hypothesis, there should only be a 1% chance of getting a mean value that's in this area. So in other words, if the null hypothesis is true and we get a sample mean that's all the way out here in this area, it is extremely unlikely. There's a 1% or less chance of getting a sample mean all the way out there. So if we do get a sample mean all the way out there, then we would reject the null hypothesis. All right, so that's very conceptual and abstract, so let's see how it works in a couple of examples. So first, we're going to do a confidence interval for a proportion. So a published clinical trial data established that 85% of patients using a standard of care inhaler experienced symptom relief within 2 weeks. A hospital's research unit runs a single-arm pilot trial of a new inhaler, no control group, typical for an early phase study before a full randomized trial is funded, and they enrolled 150 patients. Of those, 118 experienced symptom relief within 2 weeks. So we're going to test at the alpha equals 0.05 significance level whether the new inhaler's rate differs from the established 85% benchmark of the standard of care for inhalers. All right, so this, another word for this is our significance level. Significance level. Okay. So first we're going to find our sample proportion. And so to do that, we need to identify what X is and what N is. So X, like in binomial distributions, is the number of successes. So in this case, the number of successes is 118 people did experience relief within 12 weeks, and that is out of 150 patients who were tracked. And so using that, we can find our p hat equals 118 over 150. So I'm just putting that in my calculator off screen, and I get 0.78, and then it would be a 6, so I'll round it to a 7. All right, and that's a 7 as well. So since alpha is 0.05 and the problem is asking just, is it different? Is it different? So that means that we're going to choose our null hypothesis. Our null hypothesis. We're going to say that the population proportion is equal to that established 85%, and our alternative hypothesis, we don't have a reason to think that it should be greater or lesser. Like, it could be either way. I mean, ideally we would have a greater proportion. If it's a new inhaler, you would want it to be like improving people's chances of relief, maybe reducing side effects or something. So there's other things that could be weighed besides like the proportion of people who experience relief, although that is certainly an important one. So let's say the proportion is not equal to 0.85 is our alternative hypothesis. And you're going to do that based on words in the problem. So this says differs, so it doesn't say less or more or at least or at most. So we're just going to do not equal to, right? So differs means different, then means not equal to, not equal. All right, so this means that this is a two-tailed test. Two-tailed test. And so since alpha, we have to divide alpha in 2 for a two-tailed test. So we're taking alpha and we're dividing it by 2. But technically we already know the critical values for a two-tailed test. If we go over here to our previous screen, the two-tailed test alpha, when alpha is 0.05, that is our critical value of plus or minus 1.96. And that's already accounting for that alpha is split into 2.5% in each tail. So we're going to use the critical values of plus or minus 1.96. All right, so here, going back, we're going to say that our z of alpha over 2 is equal to z of 0.025, which equals plus or minus 1.96, because this is a two-tailed test. That's the only reason why we're dividing in alpha over 2 is because it's a two-tailed test. All right, so in order, our goal now is to test this critical value. So what this critical value means is on the standard normal scale, right, where 0, our mean is 0 on the scale, and we have minus 1.96 and plus 1.96. That means that my critical regions are these areas over here that have 2.5% of the area in each tail is beyond the z-scores of 1.96. So if we get a z-score this is our rejection region, if we get a z-score that is more extreme than plus or minus 1.96, in other words, in these yellow areas, then that is too extreme to consider that it came from the null hypothesis. So we would reject the null hypothesis. But let's see what happens. Let's see what z-square we're going to get. But first, we have to calculate the standard error. So in this case, we found we used the population proportion. We calculated the population proportion above. But now, down here, we're going to use the proportion, not p hat, but we're going to use p, so that's 0.85, which means that q is going to be 1 minus p equals 1 minus 0.85 equals 0.15. Let me draw a little line here. This is like talking about our critical values and our critical regions. All right, so that means that the standard error is going to be the square root of 0.85 times 0.15 over the square root of n. So I'm just going to do that off screen while I do 0.85 times 0.15 equals divided by, I wrote n, but we actually want to say what n is, and it's the same n because this is a sampling distribution for samples of size 150. Right, so I'm going to divide that by 150 and then square root it, and I get 0.02 915, so I'll do 92. So 0.0292. And this 2 could be a bit better. So make that look more like a 2. All right, so that's the standard error. So now I'm going to do the z-score. The z-score, z, is going to be equal to where my sample statistic falls on the distribution of the null hypothesis. So the null hypothesis distribution is based on a proportion of 0.85 and the n equals 150. And so the standard error, this is for the sampling distribution in the null hypothesis. All right, so that's the mean of the sampling distribution, or the proportion, and then dividing it by 0.0292. So just doing this on my calculator, 0.787 minus 0.85 equals, divided by 0.0292. And so here I get negative 2. It says 157, so I'm going to round it to 16. Okay, so that number is actually more extreme than my critical value. So in other words, this z-score that I just calculated, so this is my test statistic. So the test statistic is the z-score based on my sample proportion, right? The test proportion. And so negative 2.15 is out here. That is in the critical region. Oh, sorry, negative 2.16. All right, so this is in the critical region. So therefore, it's this fancy symbol, but we're going to say therefore reject H naught. So we can say that the proportion who experience relief in 2 weeks is different from the established 85%. So the proportion, I don't really have a lot of room to write this here, but the proportion is different. From 85%. Okay. And so now let's look at, so that's for a proportion, and it's going to be the same process for the mean. The only difference is that we would calculate the sample mean here, but that's usually going to be given to you in the problems for this class. And the formula for the standard error is a little bit different. Otherwise, it's the same steps, same logical process. So here we have CDC, National Center for Health Statistics, reference data drawn from national health surveys establish a mean resting heart rate of 72 beats per minute for middle-aged and older adults with sigma equals 9 beats per minute, sigma being the symbol for the population standard deviation. So sigma means population standard deviation. So since we know that, that means that we can still use a z-test. A medical research group is studying whether a structured cardio program for seniors is associated with a lower resting heart rate than the general population norm. They sample 36 seniors who have participated in the program for at least 6 months. The sample mean resting heart rate is 68 beats per minute. Test at alpha equals 0.05 whether the program participants' mean resting heart rate differs from the national norm for their group. Okay, so in this one, we would have to calculate the sample mean if you were the researcher, which you would probably have technology do that. And so in this case, it's given to us that it's 68 beats per minute. We also know that the sample size is 36. We're going to use that later. And that the population standard deviation is 9. Oh, I wrote PM, but it's BPM. BPM. Okay. So we have the mean. Now we just need to, based on we need to establish the hypothesis, null and alternative hypothesis, in order to know what critical values we're going to use. So here it says test whether the heart rate differs. So again, it's saying differs, so we're going to use a two-tailed test. So we're going to say that the null hypothesis is that the population mean is equal to 72 beats per minute, and that the alternative hypothesis is that the mean is not equal to 72 beats per minute. And so with the same alpha equals 0.05, we have the same alpha over 2 equals 0.025. So we have the same critical values, which are z of 0.025. Well, I guess we'll say that one's not going to be plus or minus, but let me put it this way. The critical values are based off of the negative version, which is negative 1.65 for the z of 0.025, but then we also have the positive version because we have so this is our distribution under the null hypothesis, where 0 is the mean, and so we're still looking for the critical values of plus or minus 1.96. So that's where it cuts it off, so that we have our critical region here is 2.5% of the data is in each tail. Those are the rejection regions. Okay, so those regions are too extreme to really be considered realistically from the null hypothesis. Under the null hypothesis, those areas are very unlikely to get a test statistic in those areas. Okay, so we can move to calculating the standard error. So the standard error is going to use what we already listed up above. So that's just going to be taking the population standard deviation of 9 beats per minute and adjusting it to a sampling distribution for samples of size 36 square rooted. So fortunately, that's very nice. The square root of 36 is 6, so we have 9 over 6, and that is 1.5. So the standard error is 1.5. So then I'm going to go ahead and calculate the test statistic. So the test statistic is z, and that's going to be equal to the mean, which is 68, minus the null hypothesis. So I should say the sample mean is 68, the null hypothesis mean is 72, and the standard error is 1.5. So just doing that on my calculator, I get 68 minus 72 equals divided by 1.5. And so I get negative 2.66666. So I'm going to round it to negative 2.67. So this critical value, if I extend my image here, is also going to be, this test statistic is more extreme than, it's going to be somewhere out here, more negative. So this is the z for the test statistic, somewhere out here, more negative than negative 1.96. And so that means that this z is in the critical region. So we're going to reject H naught. We're going to reject a null hypothesis. So that means that we can conclude that the mean resting heart rate for these seniors, so for like the participants, so like the sample population, like the population that was sampled from. So the mean resting heart rate for the participants is different than 72 beats per minute. Right, so we rejected the H naught, that the mean is actually 72 beats per minute. So then you're like, okay, maybe it's not that. What do we do? Well, you have your sample average. You might construct a confidence interval and say, well, for this population that we got these participants from, the mean resting heart rate is somewhere in this confidence interval. All right, and that is it for now.